Okay, so let's get started. So as you all know, the final exam is tomorrow. I will send out an email later today explaining logistics, but I already announced this many times. I will hand it out on Moodle tomorrow morning, somewhere between 8 a.m. and 9 a.m. and it will be due one day later. Yes. And it's open book, open notes, but obviously you can't discuss it with anyone except if you have questions, you can ask me. Okay, uh, so that will be the end of the exam, but the lab which many of you have yet to turn in, as I said, I can accept all the way through next week. Okay? The earlier you turn it in, the easier it is because I have a hard deadline to turn in the grades early week after next, so that I cannot change. So if you can hand it in somewhere towards the latter part of next week, that would be good for the TA to finish grading and we can hand out the grades. Okay? I'll send a note about that as well. So this is the last lecture. I was initially thinking maybe I'll do a review of all of the topics we studied, but I figured that might be a bit boring. So I instead decided to spend the lecture on a topic that I was actually going to skip initially. It's a topic in the book which is distributed security. The reason I was going to skip it is now there is a graduate level course on security which goes through all of those concepts in a lot more detail. But I figured that it's worth spending our last lecture so that you get a little bit of sense of what this topic is in case you don't end up taking this other class which is on security. So that's what I'm going to do. And so we will talk a little bit about basic concepts in security, and then I'm going to talk a little bit about applications that are important from a distributed systems perspective that might be somewhat of interest to us in this class. Okay, so first let's start with some basics. So basics, I'm going to talk a little bit about authentication, encryption, and things like that, which are basic concepts in security. Authentication is basically the problem of one party convincing the other party that they are who they claim to be. Okay, there is an example that basically you get a phone call from someone claiming to be your bank and ask you for some information. How do you know that that's the bank as opposed to somebody masquerading as your bank? Okay, same is true if you uh, go to a computing system and claim to be someone. How is the system to know that you are that user and not someone else? And that's really the problem of authentication. Okay, so there are many techniques that you can use to address authentication. I'm going to go through some of them quickly. You should be familiar with all of them. Okay, so clearly just telling someone that you are someone doesn't help. Okay, so you can, if Alice wants to authenticate herself to Bob and just says, I am Alice, Bob doesn't know whether to trust that or not, because there could be a third entity, an intruder, Trudy, who can send the same message. Hey, here Alice and Bob are computers. Security world, they like to have personal names assigned to entities rather than saying they're two computers. So intruder Trudy can also send the same message, and Bob doesn't know whether the message actually came from Alice. So there are ways to address this. You can use IP address to do a better authentication, saying if a packet came from some machine claiming that it's from Alice, can you use the IP address to claim that the packet actually came from that machine, so it must be from Alice. That doesn't quite work because it is very easy to do what is called IP spoofing, where when you send a network packet, you can change the source address on the packet to whatever IP address you want to be. So when the packet reaches the other machine, it actually appears to have come from a different machine than the one it was sent from. So if you can spoof IP addresses, which is quite easy if you just actually change some code in the OS kernel, so that when the code packet goes out, it simply replaces the IP address. Instead of the IP address of that machine, you put whatever random address you want. Then this is going to defeat IP address based authentication. So that's obviously not going to work. And the technique that most authentication protocols are going to use is, if you claim to be Alice, you have to then supply a password. Okay, so that is how you log into a system. You give your username, system prompts you for a password saying prove it that you are whoever you claim to be. and then if you supply the right password, then the system lets you log in. Okay, so you may then, the assumption is the password is only known to you. So if you could supply that password, it must be you, not someone else. Okay, that's the basic idea. That is at the heart of most of these authentication protocols, but there are some problems even with that, as we will see. So for example, if Alice sends a message packet or a message to Bob saying, I'm Alice, here is my password. Okay, if you use a protocol like Telnet or FTP to do this, what happens is all of the text in your packet goes unencrypted. Okay, so your username is going in plain text unencrypted. Your password is going in plain text and unencrypted. So although you have proved to Bob or your computing system that you are Alice and you have provided a password, what will happen if you send your username password unencrypted is an intruder can actually intercept the network packet while it is in transit and learn your username and password. And once your username and password is learned by a third party, they can then use it to access the system. Okay, so protocols like Telnet, FTP are not secure in that sense because none of the communication is actually encrypted between the two systems. So your username, password, everything goes in plain text, and that doesn't work. Okay, so the side thing you should keep in mind is not to use unsecure protocols like Telnet, which is why I don't know if any of you know what Telnet is first of all, but it is the predecessor of what you now use using SSH and so on, which are more secure versions. Telnet was just a way to remote login, connected to a machine and you log in. Exactly what SSH does, but SSH is more secure. Okay, so you shouldn't send username passwords in plain text. So what could you do? You have to encrypt packets so that an intruder cannot figure out what is being sent, so that your passwords are not compromised. So here is an example way to do this. Okay, so we will assume that Alice and Bob use what is called a symmetric key. Okay, a symmetric key is a secret key that is only known to Alice and Bob, and they can use this key to encrypt the message. Okay, we haven't talked about encryption yet. I'm going to come to that, but you know the general idea. Okay, encryption allows you to take some message, apply a key and a function, and it gives you a scrambled or an encrypted version of the message. Okay, and then you can use the same key to recover the original message or decrypt the message. Okay, so only Alice and Bob know the secure key. So here is a new authentication protocol where Alice sends a message to Bob saying, I am Alice, which is encrypted. Okay, so Bob can now decrypt this message, and what you see in the message is I am Alice. Okay? Now, since this key is only known to Alice and Bob, okay, Bob can assume that if you decrypt the message and you get a username saying Alice in there, only Alice would have sent that message. Okay, because the key is only known to the two of them. Okay, so this is one way you can authenticate yourself, okay, using encryption. However, even this protocol, which is now using encryption, is problematic because it is vulnerable to a kind of attack. Okay, for example, if this encrypted packet, you're saying, so the encrypted packet is simply this message, I am Alice, encrypted in some form. If the encrypted packet is intercepted by an intruder, okay, the intruder can simply hand over that packet at some later point in time to Bob, and Bob will believe that that packet came from Alice. Okay? This is what is called as a replay attack. Okay? You are simply storing. So the intruder cannot generate, the intruder doesn't know the key, they cannot generate such a message. However, they can intercept an encrypted packet and then hand it to Bob at a later time, exactly this encrypted string saying I'm Alice and claim to be Alice. Okay, and Bob will have no way to distinguish whether it actually came from Alice or not. So this is referred to as a replay attack. That can also happen. So even when you use encryption, you have to be careful because you can be vulnerable to things like replay attacks and so on. Okay, so what could we do? So you shouldn't send your passwords in plain text. You shouldn't, even if you send, so this could also be extended to say I'm Alice and here is my password incidentally. Here you're only saying I'm Alice, but assume that username and password are both encrypted and sent over. Okay? But somebody is just intercepted those encrypted versions of the packets and then is just simply replaying them at a later time. Now you're stuck. So what could you do?
nonce or sequence number too?
Okay, add a nonce or a sequence number. So we'll talk about that next, as to what that is. So essentially, if you want to make your protocol really secure, you shouldn't reuse passwords at all. Okay, the basic idea is either the password should never be sent, or you should use a different password each time. Okay, and by password I'm using the word password in sort of a very broad way. What you're using to authenticate should never be reused at some later point in time, so that even if the intruder intercepts those packets, encrypted packet, simply presenting them at a later time doesn't allow them to authenticate to Bob. That's the basic idea. Yeah, so you can use a one-time password which is never reused again, or we are going to use something called a nonce, which is exactly the same idea. Okay, so we are going to use a sequence of passwords, and this is how it's going to work. So we are going to use what is called a nonce. A nonce is once in a lifetime integer. Okay, so which means that every time you say I want to generate an integer, you can generate a random number, but next time or any subsequent time you generate another random number, you'll never repeat it. Okay, think of a sequence of integers you generate, but they never repeat. Okay, so we'll call such a number integer as a nonce. Okay, it's a once in a lifetime integer which is never going to repeat over the lifetime of this application. Okay, so the encryption protocol now is Alice is going to send a message to Bob saying I'm Alice. This is unencrypted, doesn't matter. Okay, Bob is going to generate a once in a lifetime integer called n. Okay, this is our nonce. So you'll say here's an integer. Okay, so that's going to go to Alice. Alice is then going to take that nonce and encrypt it with the session key that is only known to Alice and Bob. Okay, we still assume that there is a symmetric key that's only known to these two parties. So you are going to encrypt that nonce and send it back. So here is the encrypted version of your integer. Okay? Bob is going to then decrypt that message, and if that message, the decrypted message has the original nonce, Bob knows that it's Alice. Okay? Now in this case, if you actually intercept, if an intruder intercepts the encrypted version, okay, and later on tries to replay the steps, saying claim to be Alice, okay, and then Bob is going to send a new nonce at that point. That nonce is not going to match the old one. So say representing the encrypted version of the nonce is not going to help you authenticate anymore. Okay, so this technique is not going to have the replay attack problem, because every time you basically repeat this authentication, a new nonce will be generated. So the encrypted message that goes back to prove that you are Alice will be different. Okay, so in other words, you are using a different password. Here the password is the encrypted version of the nonce every time to authenticate yourself. Is that clear? Okay. So this is also called challenge response protocols. Okay, if you actually work in a company and subsequently in your life career, you will see that many of them use firewalls and so on. And if you are outside and you want to access some computers inside the firewall, you may be given some protocol, and many of them will use what is called a challenge. Okay, so you basically say I am a user X. Okay, system will say here's a challenge, and the challenge is going to be a nonce, saying prove to me that you are who you are. So you'll get an integer back, and you are supposed to send back an encrypted version of that integer. Okay, that is how you use the session key. Many times the session key may be actually encoded in a device. So you may get a tiny device where you punch the key and it gives you back an integer, or it displays an integer. That is what you actually give it back. So you don't need to carry the key with you. It's actually in the device that is given to you. Okay. So here is encryption protocol that is actually secure. Okay, now the security of this protocol, of course, depends on the ability to generate nonces that are never going to repeat at all. Okay, so even if it's 10 years later or 50 years later, if you go and authenticate, you will always get a nonce that is never repeated. So you have to ensure that the integer is long enough. Remember that in our computing representation, integer is a fixed bit representation. So if you have a 32-bit integer, you only have so many integers you can generate before you run out of values. Okay? So if you use 32-bit integer, you better be sure that the lifetime of the application is such that you will never run out of a new 32-bit integer that has never been used again. Okay? Or you can use a 64-bit integer. Whatever you pick, there is still a limited number of integers you can generate because of the fixed bit representation of a nonce inside a computing system. Okay, so these are all practical issues you have to deal with. Any questions here? Okay, so another way to do this, rather than using nonces, is well, it does use nonce as well, but another way to do this without having to use symmetric keys or use what is called public key cryptography. Okay, this is a very popular technique as well, and what it uses is, rather than having a shared key, a symmetric key between Alice and Bob, you are going to use something else called a public and a private key. Okay. So in this case, public key cryptography says if you're a user A, okay, you can generate a pair of keys. Okay. One is called your public key, another is called your private key, okay, which are used for encryption and decryption. Okay. So you can take any message, and the assumption is that the private key is going to be only known to you. The public key is published. Okay. Everyone in the world can get your public key. You actually give it to whoever wants to get your public key. Okay. And if you want to send an encrypted message, what you're going to do is you're going to take a private key and use it to encrypt the message. Okay. So this is going to give you an encrypted version of the message and prime. Okay. Then you can send that message to anyone. And since the public key is known, they can actually take your public key and take that message, and then that will give you back in. Okay, so these are, so if you take the public key and put M and get M prime, you can use the private key to extract M back, or if you use the private key to encode M, you can use the public key to get it back. Okay, there in that way, just as in a symmetric key, you can take a value, you can apply the symmetric key to it, you get an encrypted version, then you can apply it back, you get the original message back. The same is true here. Okay, all encryption algorithms are going to do the same thing. They will have a key, okay, they will scramble the message, give you an encrypted version of a message, and then if you apply a key again, you'll get the original back. Here, rather than using one key to encrypt and decrypt, you're using two keys. Okay, one is called a public key, and the other one is called a private key. Okay. There are many techniques to generate public and private keys. One is called RSA, which you may have heard of, okay, but I'm not going to go into RSA here. Okay, but just keep that in mind that RSA is an example of a public key cryptography. If you use SSH and so on, you'll know if you ever generated a key of your own, you'll know there's a public key and a private key that you use in SSH. Okay, same concept is true here. Okay, so if you assume you have a public and private key, okay, which here is called the encryption key and the decryption key. Okay, EA is the encryption key of Alice, DA is the decryption key of Alice. Okay, and so all public key cryptography have this value, with this property rather. If you take N and apply the encryption key and then the decryption key, you get back N, and this is, you can apply them in either order. That's exactly what I had said there. You can take N and first apply D of A, that will give you N prime, and then if you apply EA to N prime, it will give you back N. Okay, so in that sense, they can do the same thing. Now with that, here is how this authentication protocol is going to work. Alice can send a message to Bob saying, I'm Alice. Okay. Bob is going to say, here is a once in a lifetime nonce, prove to me you're Alice. Alice is going to take her private key, which is only known to her, and encrypt that nonce and send it back. Okay. So what Bob can simply do is take Alice's public key, which is known. Okay, so Alice publishes her public key. So Bob knows the public key, and so all Bob has to do is take Alice's public key, apply it to the encrypted version of the nonce, and if you recover the nonce from it, then you know that this came from Alice. Only Alice has access to her private key. Okay, so Bob can verify, and as can anyone else for that matter, because the public key is known that this could have only come from Alice. Okay, so this is a authentication protocol, the challenge response authentication protocol that uses public key cryptography. Any questions on this? Is this clear? What I just said, okay. So public key and private key, although I'm not going to go into any encryption techniques, I'm going to briefly mention in a minute or two how public key cryptography can work. So, or any encryption algorithm. So let's say you want to encrypt some message, okay, of arbitrary length. What you do is you take that message and you chop it up into blocks, V1, V2, V3 and so on. Because it's an arbitrary string, you will chop it up into blocks and you will take each block, okay, and you are going to encrypt it. Let's say you take your encryption key, and you encrypt it. So this will give you a B prime. This will you apply the encryption function. It will give you B2 prime, and so on. Okay, so this is now the encrypted version of the message. This is what you can send to someone, and what they now need to do to recover this is to apply the decryption key. So B prime will give you back B1. This is going to give you B2. This is going to give you B3, and so on. Okay, so this is how most of these encryption algorithms are going to work. They are going to use, if you have symmetric key cryptography, the encryption key and decryption key are one and the same. Okay, because it's the same key, and the assumption is the key is only known to the two parties who are communicating, not to anyone else. So no one else can take B prime and try to extract or generate B prime to begin with. Okay? In public key cryptography, these are two different keys. Okay? So if you are sending a message to someone, you can use their public key, which you know, encrypt it, so that only they can decrypt it. Because the private key is only known to that party. So if I want to send a message to a colleague, I will use their public key, which everyone knows, and including me, encrypt the message, send it to them. And I'm assured that only they can decrypt it and figure out what the contents are, because only they know the private key. This is how I would send an encrypted message to someone. Is that clear? Okay, I'll come back to using this in a little while when we do secure email and whatnot. Okay, so here is a problem with using public key cryptography. Okay, so let's say we want an intruder to impersonate Alice. Okay? So the intruder is Trudy. So Trudy is going to send a message to Bob saying, "I'm Alice." Okay, Trudy is impersonating Alice. Okay, so Bob is then going to try to send a nonce back to Alice, which Trudy is going to intercept. Okay, it's a network, so you can just intercept this message. Now, what Trudy is going to do is she has to send an encrypted version of the nonce. Okay? Trudy is going to use her private key, not Alice's private key, to encrypt that nonce. So you use the private key, that's why it says D of T. He sends the nonce back. Okay? Now, for Bob to authenticate that this is Alice, Bob needs Alice's public key. Okay? So the assumption is that Bob doesn't have a database of everyone's public keys. Okay? So Bob has to go and get the public key from somewhere. Okay? So Bob is then going to basically somehow try to get Alice's public key. One way to do this is to send a message to Alice saying, "Give me your public key." Okay? People put up their public keys on their website. As you may have seen, if you go to some website, they'll say, "Here is my PGP key, okay, which is my public key." Okay? That's the way. So basically, let's say Bob goes to Alice's web page to get her public key. Okay? Now, Trudy can now intercept that message, or can actually go to the web page and change the public key as well. Okay, so in this case, we are just simply assuming that Trudy is able to intercept this attempt to get Alice's public key and instead send her public key instead, claiming to be Alice's public key. Okay, so Bob is going to get Alice's key. Trudy intercepts that request and sends her key, saying this is Alice's key. Okay, Bob doesn't know this, so Bob assumes that is actually Alice's key, and then you basically use Trudy's key instead of Alice's key to decrypt that message. The nonce comes back, and you think that Alice has actually sent that message to you. Okay. So this is referred to as also man in the middle attack and so on. Okay. So it basically allows you to impersonate others. Okay. So what has happened is this is not a problem in public key cryptography. Okay. The problem is that key distribution is the issue. Okay, so any encryption algorithm is only going to be as secure as a key distribution. Okay, so you need not only a good encryption algorithm, you also need a secure way to share keys. Okay, so here the problem was that Bob did not have a good way to get Alice's public key, and you were able to break the protocol at that point in time. Okay. So this is equivalent to you want to protect your home, you buy a big lock, okay? You lock your house and you keep the key under the mat. Okay, so now if the key is not secure, the lock is not going to be secure either. Okay, same problem. The encryption algorithm is secure, but key distribution is not secure. So if you can get somebody else's key or impersonate your key as someone else's key, then there is a problem with the protocol. So this is something to keep in mind. Many secure protocols get broken not because there's a problem with the protocol, but there's a problem with how keys are distributed. Okay. Alright. So this is exactly what I was talking about, man in the middle attack, which is this previous protocol. I'm going to skip that. Okay. But that's a problem. Okay, when we come back to setting up SSL connection between a browser and a server, we'll come back to this problem. If you are able to impersonate the server certificate or key, you will actually have the exact same problem, okay, where the server is sending messages that can be decrypted and re-encrypted. Okay, so I'll come back to that in a little while. So let me now talk a little bit about digital signatures using public key. Okay, so goal of a digital signature is to sign a document using an electronic key rather than just as you sign a piece of paper. Okay, you want to have a digital signature that you can assign to a piece of paper, electronic document, which serves the same purpose. Okay, that somebody can verify it's your signature and that you actually signed it. And once you sign it, you can't claim that you did not sign it. Just as if you write a check, send a check to your bank, if the bank validates that your signature on the check matches the signature there on the record, they will cash the check. Okay? And you can't claim if the signature is actually authentic that it's not your signature. Somebody makes a bad impersonation, you can say this doesn't match, so you did not do a good job matching the signature. Same is true here. If you send a signed document, the other party should be able to verify that you signed it. Okay? And if you actually signed it, you should be able to, you shouldn't be able to claim to the other party that you did not sign it. And a third is if the document is actually altered, okay, or somebody is trying to alter it, then you should be able to say that's not what the document I signed. So you need all of those properties. And the simple way you are going to be able to do this is take a document which we'll call message M. Okay, it's an arbitrary length string. Any document can be thought of a string or a set of bits of arbitrary length. You can simply take that string and sign it with your private key. Okay, you can encrypt it with your private key. Okay. And you can present this encrypted version of this string to anyone saying this is a signed version of the document. Now, since your public key is well known, anyone can verify that you signed the document by simply taking your public key, which is here, applying it to the encrypted version of the document, and the original document will be recovered. This will tell them that only you could have encrypted the document in that way. Okay? If somebody else encrypts the document, that will be a different encrypted version. Okay? That will be a different string. So you can simply look at the encrypted version of the document, take your public key, and verify that you could have signed it, that you have signed it. You cannot claim you did not sign it because only you know your private key. Okay, so D of M or DB of M is a string that only you could have generated, given M. Okay, so this basically gives us all of these properties that we want. And you cannot fake a message. You have repudiation, which says you cannot claim you did not sign it if you actually signed it, because you know your private key or a document that is actually signed by your private key. It's encrypted with your private key, so you can't claim you didn't sign it and so on. Okay. So this is the simplest form of a digital signature. You can simply use public key cryptography and encrypt any document, and that's equivalent to you having signed it. Now this happens to be extremely expensive computationally. So we are going to see some ways by which we can make it more computationally efficient. And the reason for this is public and private keys are very long keys. So the longer the key, more computationally expensive is it to encrypt and decrypt. Okay? And in some cases the keys may be 124 bits long. So that's going to make it very expensive to encrypt and decrypt documents. So the question is, can you take the same idea that we had on the previous slide, but develop a more efficient version of a digital signature? Okay, so let's see how you can do that. So one way to do this is to actually not sign the document itself, but sign a hash of that document. Okay, this is going to be called a message digest. Okay, message digest is a summary of the message. Digest essentially means summary. Okay, so you take any arbitrary license document. Let's say it's you write up your exam, final exam. Let's say you wrote 25 pages of your exam. Okay? Then you want to sign it saying I actually submitted and I'm sending you a signed copy. Instead of encrypting a 25-page long document, which is going to be computationally expensive, you can first hash that 25 pages into a summary of the document, which is a fixed length hash. Okay? Then you can simply sign the hash. You can send the document and the signed hash, which can then be used as a digital signature. Okay? That's the exact idea here. So what you do is you take the document M. The first thing you are going to do is apply a hash function, which will take a variable length string, any arbitrary length document, and convert it into a fixed length hash. The hash will be a fixed length, let's say 512 bytes or some smaller string, as opposed to an arbitrary length string. And then what you take is you take hash of M, and you're going to digitally sign it. This is you're going to just take your private key and sign or encrypt hash of M. Okay, and then you're going to send M, which is unencrypted, and a signed version of the hash saying here is the document, here is a signature. Okay, so in this case, this string here, which is the signed version of the hash, is your digital signature. Okay, so now you can still verify that you signed the document because anyone else can take this document M, okay, convert, first generate hash because the hashing function is well known. You can just take the document and generate the hash. Okay? Then you can take the person's public key and apply it to this string, which will recover the hash. And you compare the hash. So you take h of m, you take the public key and extract h of m here, and if the two match, it proves to them that you must have signed the document. Okay, is that clear? So if m is altered by someone because m is unencrypted, okay, you will get a different string m prime. Okay, so if now the hash m prime, that will generate a different hash. So when you extract the hash from here, the two will not match. This allows you the protection to claim that you never signed the altered document. Okay, you can say I signed a document that generated h of m. If m has been modified and is going to generate a new hash h of m prime, the two are not going to match. So you don't have to, nobody can claim that you signed the altered document. Is that clear? Now the reason this is computationally more tractable is signing a fixed length string or encrypting a fixed length string is obviously going to be cheaper than signing an arbitrary length string, which is an arbitrary size document. Okay, clear? We'll come back to all of this and try to put it together in an application that you probably know about, which is secure email. We will look at encryption, signatures, and try to put it together and see how can you send a secure email to someone. Okay, but it requires that you understand what is a message digest and whatnot. Okay, so now in order for all of this to work, you need a hashing function, a good hashing function with certain properties. Okay. The most important property you want is you don't want the probability of the collision. You want the probability of hash collisions to be very, very low. Okay, because remember, you are not signing the original document. You are signing the hash of that document, which is a fixed length string. If an intruder could find another document, okay, an arbitrary document which hashes to the same value, they can then claim that you signed that document. Okay, so in other words, if there's a hash collision, if two values, or so let's say your m and m prime, okay, if hash of m and hash of m prime are one and the same, and you are actually signing hash of m, then the intruder somebody can claim you signed m prime instead. So you want the probability of hash collisions to be low. Okay? Any hashing function, as you realize, will have collisions because you are taking arbitrary length strings and mapping it to fixed length values. That fixed length values can only hold a certain number of values. Okay? So given an infinite set of documents, then you're mapping it to a finite set of hash values. So there will be collisions no matter what, but you want the probability of that collision to be as low as possible. Okay? Second, what you don't want is the reverse to be possible. Given a hash h of m, you shouldn't be able to generate a string that is going to give you that value. Okay, so I gave you a hash. Let's say hash is 32. Okay? If you can now generate all possible strings so that if you apply the hashing function, it generates value 32 or any string for that matter, That also breaks this protocol because now you can actually give an h of m, generate m prime that maps to here. And then you can claim that you signed some other document, which also you don't know. So these are all properties you want. It's infeasible to find messages x and y such that h of x is equal to h of y, or given a digest x, it should be infeasible to computationally create y such that h of y is going to be x. Okay, so you want good hashing functions with this property. So all of these digital signatures are going to be based on our ability to choose a good hashing function that has these properties. Okay, without that, you are not going to be able to do this well. Okay. There are many hash functions. There's one called MD5, which stands for Message Digest 5, which I'm not going to go into. It also uses a key and it uses an arbitrary length string to generate a fixed length string. But in the interest of time, I'm going to skip MD5, mostly because MD5 is no longer used in practice. It's not a secure hashing function anymore. It uses 56-bit keys, and you can now launch brute force attacks to break it. So what brute force attack means is you can start enumerating every possible string and use the hash function. Because MD5 is a well-known hash function. The hashing function is known. If I could list every possible string and then just hash it and find the hashed value, and I could just computationally search through all the space, I will be able to find two keys or any other string that created this hash and things like that, which you don't want to happen. Okay? So what most hashing functions do is you basically don't use smaller number of bits, you use more. Okay? The ones that are used today is called SHA hash function, which stands for Secure Hash Algorithm. Okay, so unlike MD5, which uses 56 bits, SHA-1 uses 160 bits. Okay? SHA-2 uses a family of two hash functions. One of them is 256-bit keys and the other is 512-bit keys, and that's SHA-3 and so. As you use more bits and use longer hashes, the probability of collision goes down, the probability of launching brute force attacks reduces because you need too much computational horsepower to launch brute force attacks and so on. Okay, so if you use anything like SSH or OpenSSL or anything like that, you will know that there are these hashing functions. So most of the modern encryption protocols that need any form of hashing will actually use SHA hashing. MD5, which was popular maybe 10-15 years ago, is not used anymore. Okay, but the book actually has a good description of MD5. So you're just curious to know what MD5 actually is. Okay, the book is also 10 years old, so it doesn't have any modern hash functions. Okay. So the other thing is that actually this hash function is designed by the government and NIST and National Security Agency, which is NSA. There was in fact a talk by a faculty job talk a few weeks ago, where the person came and claimed that there are some security researchers who believe that SHA function is not as secure because there's a backdoor to actually break the hashing function. And they're trying to see if they can prove that there is a backdoor. Of course, nobody has proved it yet, but they were trying to figure out, because some of the values that are chosen are magic numbers. They're integers that have been chosen. You don't exactly know how they were chosen and do they actually have some properties that you don't know about that can be used to break it. So, but be that as it may, there's just speculation by or suspicion by some security researchers. As of today, this is the most secure hashing function that's widely used. Okay? It's not to say that you shouldn't use it or something. I was just mentioning what some researchers claim or are trying to prove. Okay. So with all of that, let's talk a little bit about a secure key exchange or symmetric key exchange. This is how a client and a server would pick a key for encrypted communication. So let's say a client wants to communicate with the server. Okay. You have to first pick a key for that session. Okay. The question is, how are you going to pick a key? And we are going to base that based on a few different ideas, and we'll see how to do this. So basically, our problem is that before you communicate, you have to agree on the key. So the server has to generate a one-time session key that Alice and Bob are going to use for encryption, and then you are going to use that subsequently. Okay, so I'm going to show you two ways to do this. first way requires a third party to help you generate the key. Okay, this is called a key distribution center or a KDC. Okay. So you basically, if you want to send a encrypted message to your friend, okay, first the two of you have to decide a key that you are going to use. Okay. So one way is you approach a third party, you ask the trusted third party saying generate a key and give it to both of us. Okay, this third party is going to give both of you the same key, and you will communicate with one another using that key. Okay? And this third party in this case is called a key distribution center. Okay? So here is basically how it will work. So Alice and Bob want to communicate. Alice contacts the KDC with a message saying, "I'm Alice. I want to communicate with Bob. Generate a key for us." Okay? So the KDC is going to generate a one-time session key, which is actually here called a key for Alice and Bob. Key under subscript Alice and Bob means that it generated a key for Alice and Bob to communicate. Now this key has to be sent to both Alice and Bob so that they can start communication. Okay? You can't just send the key unencrypted. And then somebody else can intercept the key and figure out what the messages are. So the key has to be sent securely to Alice and Bob. That's where the problem arises. Okay? So in this case, what we will assume is both Alice and Bob, because they have they trust the key distribution center, they have pre-generated a key that Alice can communicate encrypt in an encrypted way to the KDC, and Bob can also communicate in an encrypted way to the KDC. So what the KDC can do, the key distribution center, is take your session key and encrypt it with the key that they share, the KDC and Alice share, which is this key here. So the session key goes encrypted to Alice. Okay, the same session key also gets encrypted to Bob, but using a different key that only Bob and the KDC know. Okay, that has to be predetermined for all of this to work. Okay, so if you have those keys set up, then you can essentially send the session key. Now the same key KA and KB is known to Alice and Bob, and they can use that for subsequent communication. Okay. So this is the equivalent of asking a third party to generate a key for you. The third party securely gives the key to you. Okay, and then you use that key to communicate. Is that clear? Okay, so sorry? That's a good point. I think so the question is, how is the first set of key distributed? Typically, you can't distribute it over a network because then that means you have to re-encrypt it. So this has to be done in an offline fashion. It's like, let's say you go to your KDC personally and then they load your machine with a key. Okay, so it's not going over any unencrypted channel. How that is done is not part of this protocol. That has to be done using a different mechanism that's not part of the protocol itself, and that mechanism has to be secure. You can't send it by email or some such thing because that's not going to work. Okay, so the assumption is you can take your machine and show up at the KDC. They will give you a key there. You put it on your machine and it's done. At that point, you have gotten a key. Okay, so but it's an important problem. That original key is not given in a secure way, you're going to be in trouble. Okay. So here is a different protocol that is not going to depend on a third party at all. Okay. So if I want to communicate with my friend and I do not want to depend on a KDC to give me the key, how do the two of us agree on a key? Okay, so no KDC involved. So here we are going to rely on, well, this one is actually the same as the other one, so I'm going to skip that. The one I was going to talk about is here. Okay, so this one is going to rely on public key cryptography. Okay. So what you are going to do is you are going to assume that each of Alice and Bob have generated a pair of public and private keys, and they published their private keys. So not the private key, that would be bad. They published their public keys. Okay. So the public keys are known. So then what Alice can do is she can say, I'm Alice, here is a nonce, and she can take Bob's public key, which she knows and everyone else knows, and encrypt these two pairs of integers or strings, saying, I'm Alice, here's a nonce, send it off to Bob. Okay. Because it is encrypted, this K plus B is actually the book's notation, but it essentially means it's encrypted with Bob's public key. So this message can only be decrypted by Bob because only Bob has his private key. So Bob will decrypt the message, and in the message is going to say, I'm Alice, here is a nonce. Okay? So what Bob is going to then do is generate a new nonce, a second nonce which is called R of B, and then also generate a key, randomly generate some key, A, B, and then encrypt the entire message saying, here is your nonce back, okay, that you sent, here's a new nonce, okay, once in a lifetime integer, and I also generated a key that we can use. And all of these three entities are then encrypted with Alice's public key, which Bob knows. Okay, so now this message can only be decrypted by Alice. Okay? So Alice is going to get the message. She is going to find that her nonce has come back. So there's no replay attacks. Okay? You're using nonces to prevent replay attacks because we'll never reuse that nonce. So your nonce came back. Bob also sent a nonce so that you cannot do a reverse attack in reverse, and you got a key. So then what Alice is going to do is take the nonce that Bob sent. Now she is going to then encrypt it with the session key and send it back. Okay, so then Bob knows the session key. Bob can figure out that the nonce that he generated has come back. So you exchange nonces two directions. You generated a random key that you sent in a secure way. Okay, is that clear? This doesn't involve a KDC. Two parties are agreeing on a key. Okay, by exchanging nonces, and one of them generates the key and sends it off to the other using an encrypted version. Now again, the security of this protocol depends critically on the ability to securely get public keys. Okay, so we are assuming that public keys are well known, but I mean, well known doesn't mean you have everybody's public key sitting on your computer. You're going to get it from somewhere. Okay, and that has to be in a secure way. So if you go to somebody's website and download it, you better be sure that whatever public you're downloading hasn't been tampered with. Nobody broke into the web server at midnight and replaced that key with somebody else's key. So when you actually get the key, you are getting somebody else's. So although people publish their public keys on their web page, it seems to be quite popular. It's not a secure way of distributing public keys at all, because there is no security. In fact, the HTTP may not even be secure. You may be sending unencrypted HTTP message. That means even in transit, somebody could alter your HTML page and send you bad content. Okay? So the assumption here is there is a way to actually distribute public keys securely. Okay? How to do that we will look at. Okay? So, I mean, all of these ways by which saying I go to somebody's web page or they send it to be encrypted by email doesn't work. Okay? What you need is something called a certificate, which you probably must have heard of. That's the only secure way of actually distributing your public key. Okay. So now let's look at how you do this using a trust. So here is the secure way of actually extracting public keys. Okay. So here what we are going to do is we are going to assume there's a trusted server that is responsible for distributing public keys. Okay. So if you want to go to get a public key, you are going to go to the server and ask for the key. So Bob and Alice want to communicate. They don't know each other's public key. They go to a trusted server and say, give me your public key. So the way you're going to do this is you're going to send a message to the trusted server saying, give me Bob's key. You are assuming that you know the server's public key first. And you send that message. And the trusted server looks up the database and sends you saying, here is Bob's public key. And since the server also not Alice's public key, it is going to be encrypted with Alice's public key, so she can decrypt it and extract it. Okay. So you can use a trusted third party. In this case, it's a server to get public keys. Okay. This is the actual basis by which digital certificates are sent. Okay. Essentially, the server. This is not a way to do digital certificates, but the way digital certificates work is you want to distribute a public key. You go to a server saying, here is the public key, please sign it. Okay, server is going to sign it. So now if you present to someone else saying, the server is going to say, this key belongs to Bob and here's the value of the key. And encrypt and then sign the whole thing. So that is called a digital certificate. You can go and present that and they are going to sign it with their private key. So you can go present that to anyone. And since the certificate's public key is known, anyone can decrypt the message and then see that the server has signed it. If you all trust the server, you should then believe that that is Bob's key, not somebody else's key, because only the server could have signed that key. Okay? I'll come back to that when we do certificates and so on in a little while. Okay, so we will skip some of this. We'll talk about access control and then come back to some. So those are some basics. Okay, we talked about encryption a little bit. We talked about authentication. We talked about key exchange. So all of these are very fundamental building blocks to build higher level applications, which now we are going to start talking about for the rest of whatever half an hour that we have left. Okay. So we're going to do a little bit of a context switch here. So now we are thinking about how to implement secure networking protocols, secure applications, and so on. Okay, so let's assume you are a large company, okay, that wants to ensure that their data is secure, the servers are secure, and so on. Okay, so they will use a number of different mechanisms to ensure the security of their system. Okay, you may have things like firewalls to prevent unauthorized access from outside. We will ensure that access to anything sensitive requires a username, password. We'll also assume that any encryption, any communication from between machines is encrypted. Okay, you don't actually use unsecure channels to communicate and so on. You may also have things like access control lists, so that say here those are also called ACLs in the sort of distributed systems. So every object, which could be a server, it could be a file, it could actually be an object in the sense of a distributed object, will have with it an access control list. The access control list is simply a list that says who has permissions to access this object and what kinds of permissions do they have. Okay, so you can say somebody can read the object, somebody can modify the object, somebody can do some other operations on the object, will be deleted. So an access control list is simply a list of all the users and what operations they are permitted to perform on the object. Okay? So now if a request comes in saying do the such and such to the object, you basically go and compare it to the access control list saying user X wants to modify this object. Okay? Are they allowed to do it? So you look at the ACL and say, do you have those privileges already or permissions already? The answer is yes, you go and do it. If no, then you deny. Same concept as accessing files. I mean, you've probably seen this in the context of file systems. Okay? So in Unix world, you have read, write, execute privileges on files. Okay? That's a form of it's a coarse form of an access control list, where you have only three types of entities. You have user, the Unix group, and everyone else, which is called world. And you basically say who can read, write, or execute a file. Okay? In the Windows world, you can actually specify an access control list. Okay, for every file, you can attach a list which says this user can read, write, but not execute. This other user can only read, cannot write or execute. Here's a group that has these kinds of privileges, and so on. So every operation is going to be matched against the access control list to ensure that you are actually only allowing the right users to do the right things on the object. Okay. That concept that is used in file systems is more general than just for accessing files. You can use ACLs for anything, accessing a server, accessing a piece of software, accessing any resources you have in the system, including accessing objects in the distributed object sense of the term. Okay. So this is the simplest form of security, where every operation is checked against a predefined list, saying is this user or this process or application allowed to do this? Okay. And if no, then you prevent it from doing it. And that's the most basic form of protection. But that's not all. If you take an enterprise, you will see that they use a number of different techniques, okay, to protect their data, protect their servers, and so on. So it's a multi-layered approach. So they will have firewalls. Okay, at the edges of their network, they are going to deploy a firewall. A firewall is going to simply check often based on an access control list or a rule, saying which packets from which machines are allowed to go in or out. Okay? So by default, if you aren't authenticated, you cannot actually send traffic inside an enterprise. Okay? The firewall will simply start dropping those packets. Okay? Only if you have authenticated yourself to the firewall will it allow you to access machines inside the firewall. This prevents all unauthorized users from even accessing any machines inside the firewall. Okay? So firewalls allow you to do some network protection. So you can essentially specify rules which are the equivalent of access control list that says who is allowed to do what. Okay? What ports are accessible, which machines are accessible, which users can access it based on authentication. That's one layer. Another layer is what is called deep packet inspection. Okay. Even if users authenticate themselves to firewalls and so on, doesn't mean that the traffic they send inside the network is not malicious. Okay. It may be that there's a virus on their machine. Okay. They log into their to the firewall and try to access the things inside, and then the traffic that is coming in is malicious suddenly. Okay. So to do this, you have things called deep packet inspection boxes. What they do is then they actually look not just where the packet came from, they look at the contents of the packet, which is called deep packet inspection. You don't look at just the headers, you look at the content. And you can do things like scan for viruses. Okay. Every network packet will be scanned. Okay. Or you can look for certain string which indicate it's coming from some malicious user and so on. And based on the results of your inspection, you can decide whether each packet is let inside or not. Okay. So that's sort of an evolution of simple firewalls which are going to be based on IP addresses, users, and so on. You are actually looking not where the packet came from, but is there anything bad inside every message. Okay. So those are all DPI missions. So you of course have virus and email scanners. So if you send an email, it is going to be scanned to make sure that attachments don't have viruses, or every incoming message is scanned to make sure there are no malicious JPEG got malicious, PDFs or malicious viruses inside your messages. And so that's another layer. Okay. And then there are a whole bunch of others. You can have things like VLANs, which are virtual LANs. Okay. This allows you to segment traffic that is inside your LAN. Okay. You can say this group of users can only access these machines, and these machines cannot access other machines. Okay. Typically, when you're inside a LAN, any machine can access any other machine. You want to prevent that, you can VLAN machines and group them together, and that will give you another layer of protection. And then you can have secure Wi-Fi, where your Wi-Fi communication is actually secured by a key and so on. And so you will have a set of these protocols. There are things like VPNs, which virtual private networks, which you can use to access machines securely from outside, and so on and so on. Okay, so what this is saying is, I just went through a list of things. I don't expect any of you to know anything more about them. But other than the fact that security of a set of machines inside any enterprise, whether it's a university or a company, is a complicated task. It's not like there's going to be one magic solution that will help you protect everything you care about protecting. You have to use a set of different techniques, okay, and a set of, to ensure the right levels of protection. And this is often where things go wrong, because security is such a complex task. If there is any misconfiguration or a problem in any one of them, okay, you can somehow attack that whole, then you are still able to get inside. If it was a simple task, then it would be not a problem. But since you are using a multi-layered approach, or depending on all of these things are all functioning right all the time, if there's any misconfiguration, there's any problem, then you are going to be in trouble. This is why you can still see security attacks happening despite the use of all of these technologies. Okay? So that's the thing you want to keep in mind, saying security of a distributed system. In this case, the system is a set of machines inside an enterprise. These are really complicated and challenging tasks because of all of these different techniques that have to be used or put in place to make things work. Okay. So with that said, I'm going to talk a little bit about things that you probably know about, and we'll talk a little bit about how security. So if you're accessing websites, you typically use HTTPS, okay, which essentially is layered on what is called SSL, which is a secure sockets layer. So in this case, the network socket, whatever packets you send are automatically encrypted at the network socket layer and decrypted at the other end. I'll tell you a little bit about how SSL works in a little moment. Okay. You can have challenge response authentication. Okay. So your bank or PayPal or any of these other sites now started doing what's also called two-factor authentication. Okay, when you try to access, let's say Gmail does this, if you turn it on, or Apple, if you try to specify username and a password, it will actually send you a text message to your phone with a code. Okay? So you not only have to enter a password, you have to enter this one-time code. That's actually a nonce. Okay? So this prevents someone who's intercepted your password from actually accessing the system, because in addition to your password, you need a one-time password, which is your nonce that has been sent to you. And then if you have both of those things, which is I know the password that only you should know, and you have a one-time nonce that has been sent to you to a separate channel, only then do you authenticate. And this gives you an additional layer of protection, because you cannot have, even if you had an insecure password, if you chose your password to be simply the string password, which still apparently many people do, you cannot get into the system, because if somebody just types that in, a secure message will be sent to the user's phone, which you don't have as an intruder. So you can't still access the system. So it provides additional layer of protection. So this is called two-factor authentication. Your things like one-time passwords, that means some banks use, online merchants use third-party payment systems to protect your credit card and financial information. As you know, if you're going and shopping online at some small merchant, you don't feel comfortable giving them your credit card, because you don't know what kind of system they use to store credit cards and so on. Instead, what many of these merchants do is send you off to a third party like PayPal or Amazon Payment or Google Checkout, where you may already stored your credit card, and they just ask you to authenticate to that site and authorize the transaction. So this prevents you from providing sensitive information to people, merchants you may not trust, and yet allow you to make payments and things like that. So there are a whole slew of these techniques that are used, whether it is web-based systems, whether it is online mail, and so on. So here is a picture of a firewall, which I was just talking about. So firewall is essentially a box that sits between the inside of your network and the outside of your network. So here is an internal network. This is a firewall, that's an external network. Every packet that comes in or is going out is matched against a set of rules. Okay? The rules are going to be checked, and the end result is going to be one of two things: allow this packet or deny this packet, okay, based on the rules. So if the rules say allow the packet, then the packet is let in. The rules say deny the packet is not let in. Okay? The default firewall will have two rules. Okay? The first rule will say all traffic from inside should be allowed to go outside. So anytime a packet is traversing from inside to outside, that rule will say let it go out. Okay? The second rule is any traffic that is coming from outside should not be let inside. Okay? So all traffic from outside is denied. Okay? So then basically if a random packet shows up at the firewall, it will be dropped. It will not be let inside. Okay? So those are two default rules that any firewall will have. If you actually have a home router with the Wi-Fi box or a router of some sort, it will have a built-in firewall. Those are the two default rules that are configured. Then you can add whatever additional rules you want. You can say, I want to open up all packets that come from outside should be allowed to access such and such port. If you add that rule, if a packet comes in trying to access that port, you will let it in. Okay? And so on and so forth. Is that clear? Okay, so we'll spend a little bit of time talking about secure email as an application that brings all of these concepts that we talked about together. It's just a good use case. So the goal here is that you, rather than sending your email as you normally do in plain text form, which is neither gives you any security nor confidentiality or anything like that, we want to develop a secure version of email that will give us 4 properties. First one is secrecy. Secrecy means if I send an email message to my friend, only that person should be able to read it. Nobody else who actually sees it in transit should be able to figure out what is inside that email message. That says secrecy. Okay? Second is sender authentication. Okay? If I receive an email from someone, if I receive an email from my friend, how do I know it came from them? Okay? Because email is, as you know, you get spam, people can forge sender addresses and all of that. So if you get a message, a sensitive message, let's say from your bank, okay, saying your account has been compromised or something, and then do something to, how do you know that is not a phishing message but an actual message? So you want to do sender authentication. Okay. You want to do message integrity, which says that nobody has altered this message in transit. Okay. That it's not like when the message at the mail server got hacked and the intruder is sitting and actively modifying the text of the message that you're getting. So you want a sender integrity, and you want receiver authentication, which essentially says only that person should be able to read it. Okay, no one else. Okay, is that clear? What the goals are? Okay, so now as it turns out, the concepts that we talked about earlier, okay, all of those can be simply used to implement secure email. So we are going to build it one step at a time. Okay. First, we'll look at secrecy. How do you send a secure secret message, email message to someone? Okay. You encrypt the message. We already know how to do that. You can simply use, if Alice wants to send a message to Bob, Alice is going to get Bob's public key, okay, and simply encrypt the message using Bob's public key and send off that message. Since only Bob has his private key, only Bob can decrypt the message. No one else who intercepts his message will know what is in the message. They can't decrypt it. Okay, very straightforward. Okay. Now, as I also said, using public keys to encrypt messages is actually very expensive. Okay, so if you just do that, that is not going to, your machine is going to sit and spin while you are trying to read your email. It's going to take a long time for it to actually show you what's in the message. So you want to use that idea, but in a more efficient way. So what Alice will actually do is not encrypt it with Bob's public key, but Alice will generate a random symmetric key K, okay, which is smaller than the public key and hence more efficient. And she will encrypt the message with K. Okay? And then you have to send the encrypted message, but Bob doesn't know the key yet. Okay? So you're going to send both the message and the key. So what you are going to do is you are going to take the encrypted version, okay, which is the email, the encrypted email, and then you are going to take the key and then encrypt that with Bob's public key, which you know. Okay? So your email is going to have two parts. It will have the encrypted message that is encrypted with the symmetric key, and then the key is going to be included in the email, but the key is encrypted with Bob's public key. So what this ensures that only Bob can first of all extract this key. Only Bob knows the private key. Okay. So if only Bob can extract the key, it follows that only Bob can decrypt the message that is encrypted with that key. Okay. So this is basically how you are going to send a secure message. This is the this is sort of version 1, but it's not efficient. So this is version 2, which is going to be more efficient. So every time you want to send a secure message, your mail client, not you, your mail client will generate a key. Okay? It will then encrypt whatever message text you have typed with the key. It will take the key, it will take Bob's public key, which is presumably available to your mail client. It will encrypt the key with Bob's public key and send both of them. So Bob's mail client, not Bob, but Bob's mail client will then take Bob's private key and extract the key first, and then use the key to decrypt the message. Then you can read it in text as it was sent. Okay. So this only gives us one property so far, which is secrecy. We have wanted 4 of those properties, so we have to still work to make this better. Okay. So second is we want authentication and integrity. Okay. First we will try to solve that without the secrecy part. So how do you ensure that Alice has sent this message and not someone else? And how do you ensure that the message was not altered in transit, okay, in some way? So the way you are going to do this, we are going to use a hash function. Okay, so essentially we will ask Alice to sign the message. Okay, so saying if I want to be sure that this message came from Alice, you basically sign the message. So all that Alice is going to do is take message M, apply a hash function. Okay, so now you have a hashed version of your email message. You're simply going to use your private key and sign it. Okay? So now if you send the message and the signed version of the hash, Bob can figure out that Alice has sent the message because she signed the message. You can verify that she signed the message by taking M and reconstructing the hash, because the hash function is known. We will construct H of M from M. We will take Alice's public key and extract H of M from here, and you will compare the two. The two match. It will tell you that number 1, Alice signed the message, and also second, that nobody has altered the message. Because if the message is altered, what comes to your mail client is M prime, not M that was sent. The hash of M prime will not match what is in the signature. Okay, so you know that somebody tampered with the message. Okay, so this is giving us authentication and integrity, but this is not going secure. As you see, your email client is sending M unencrypted, but is going to send a signature. This you may often see. You may get a random email where the plain, the message is in plain text, but there's a signed version of the message as an attachment. So this, if your mail client has the person's public key, you can verify that that person sent it and the message hasn't actually been modified. Okay, this is unencrypted email, but signatures, digitally signed emails. Okay, so now you can take the both of the things, which is the secrecy part and this, and combine the two. That is going to allow you to send encrypted email and also signed email. So here you are signing but not encrypting. In the previous case, you are encrypting but not signing. Okay, so that's what is shown here. Okay, so the way you are going to do is that you want to send an email message M. Okay, your mail client is going to first generate a hash of M. Okay, and then your mail client is going to sign it with your private key. Okay, in this case, if Alice is the sender, the mail client is signing the hash of M with Alice's private key. That's the signature. Okay, so then you are going to take the text of the message M and the signature. Okay, you will take that. We'll call that combined message M prime. Okay. Now we will actually encrypt M prime. And we'll use the previous technique. First, your mail client will generate a symmetric key K, and you will encrypt M prime with K. Okay, so now you've taken the email and the signature, you encrypted it. Okay. And then what you're going to do is, since the key also has to be sent, you're going to take Bob's public key and encrypt the key itself. Okay. And at that point, you're going to send K of M, which is that, and the key. Okay. And when the Bob's mail client receives this, they are going to first take their private key and extract the key. Okay. Then once you have the key, you are going to apply it to the encrypted version of the email and decrypt the email. So from the email, you are going to get M prime back. M prime is essentially the message of the email and the signature. Okay. And then you are going to verify that the signature actually is from Alice. So then you also know the email came from Alice. Okay. So if you put all of that together, you have secure email that's going to give you also the authentication property that only you can. And last but not least, it should be clear that somebody else who gets this cannot actually figure any of this out, because only Bob can first of all even extract the key. Okay, because it's signed with, or not signed, but encrypted with Bob's public key. Only Bob knows the private key, so only Bob can even see this message. No one else can see the message. Okay. So there are mail clients that actually do all of this. It requires you to exchange keys and certificates and whatnot first, and then you can actually send secure email. It's very clunky because you have to ensure that the keys are there and all of that. So it is not taken off, but most of the mail clients actually support it. Thunderbird or Apple Mail and all of them actually support sending secure email in this fashion. Any questions here? Okay, so this should give you some sense of how you can take some of what I was talking about and build a secure thing. And I'm going to show you the same thing as SSL, and then we will stop. Okay. So we talked about secure email. So next is, how does a web browser set up a secure connection to a server? Okay, and this is, so that is whenever you type HTTPS : some URL, first thing your browser is going to do is set up a secure connection in the server. So how is that going to work? So we will actually see how that works. So here is essentially your SSL protocol. Your browser is going to first send a message to the server saying, send me your SSL version number and references and so on. Typically a server will say SSL version 2, which is the latest version number. Okay? And then the server is going to send to the browser, okay, a certificate. Okay? A certificate is essentially the server's public key, okay, but signed by a trusted third party. Okay? Because for anything to happen, you first need to know server's public key. If I contact CNN in encryptor, I need to know CNN's public key. How do I get it? Okay? We are going to have the server send it to us. Okay? But because key distribution is a problem, the key is sent to us encrypted as a certificate where it's signed by a trusted third party. And as it turns out, your browser will actually have the trusted third party's public key so that you can verify that the key is accurate. It's not tampered. So the certificate will say this server is CNN, here is the CNN's public key. Okay, so in fact, anytime you have an HTTPS connection with that green lock sign, if you click on that lock sign, it will show you a certificate. and you can actually say examine certificate. It will say who is a trusted third party that signed. There are certificate issuing entities. You actually have to pay them and they will issue a certificate to you. They'll verify your identity so they don't give certificates willy-nilly. You can't go and claim, I'm CNN, give me a certificate. Okay, they will actually verify that you are who you claim to be and then give you a certificate. So your browser will actually just get that certificate, okay, and it will verify that the server is who it claims to be, and you'll also get the public key from the certificate. Okay, and so the signatures are from what are called certification authorities. There is VeriSign, there are a whole bunch of them. You can go and look in the preferences web browser. It will say, I recognize the following certification authority. These are the trusted third parties that your browser trusts. Okay, that's already built into your browser. Okay. So you will use the CA, you will verify the certificate and whatnot. And at that point, your browser is going to generate a session key K. Okay. It will encrypt K with the server's public key that came inside the certificate. Okay, because you could extract it from the certificate. It was signed by the CA. The CA's public key is already built into the browser, so you can extract the server's public key. So you generate a session key, you sign it with the server's public key. Okay, so then you are going to send a message saying all future messages are going to be encrypted. Here's the key. Okay, and then you send off the key to the server. So only the server can extract the key using their private key. Okay, and then the server is going to tell the browser all future messages are encrypted. Send the key back. Okay, you can also exchange nonces in this case if you want, okay, in certain versions. But at that point, a secure connection has been set up, and all subsequent communication will use a session key to encrypt. Okay, so this is essentially how SSL is going to work as well. Any questions here? So we have run out of time. We are going to skip electronic payments and all of that. I'm going to just wrap up here. So we are done with the class. Okay, so the very last lecture, these are all the topics we covered. Okay, we started with processes, threads, we did scheduling, virtualization, migration. We spent some time on communication and naming. A bulk of the time is spent on canonical problems, leader election, transactions, and all of that. We then did some fault tolerance, consistency, applications. In the last few classes, we looked at file systems. Last time we did middleware and set of special topics, data centers and green computing, cloud computing. We didn't actually get to multimedia. That was planned, but we canned that in the interest of it. So that is it as far as the course is concerned. As I already mentioned, as far as the final exam is concerned, the latter part of this is going to be emphasized more. Okay, the early part is still covered in the final, but it will be emphasized less because the midterm already tested all of you on that. Okay, so if you have any questions about any aspect of the class, you can come talk to me today. If you have questions during the final, send me email. I'll try to clarify the question and so on. Okay, so I'm hoping that you have gotten something out of this course. You gave me some feedback in the course evaluation, which I'm hoping to use next time. But if you have any other feedback, questions, or anything like that, come and see me. Okay, so let's stop here. We will end the course here, and I hope that you will have a good final exam, finish the lab, and then have a good summer. Okay.